Hello everyone, and welcome to the channel. In this video, we'll hook up some RAM to the computer, we'll take a look at the timing of this circuit, and we'll go through a program that verifies that all memory locations are correctly accessed. I hope you enjoy! Okay, so let's take a look at the RAM chip I'm going to use. It's one of the 62256 family of chips. This one is made by Liontech. It's a 256K CMOS static RAM, and it's going to be pretty similar in construction to the ROM chip we installed the last time. If you look at the pinout is actually identical. You have 15 address pins, 8 data input-output pins, and then the standard interface of a chip enable, write enable, and an output enable. And so those pins are going to work exactly the same as the one of the ROM chip we installed last time. So if you look at the voltages, you can see that it's also a TTL level chip, just like the ROM. So we're good on that front. And then the timings are going to be much better. So the specific chip I'm going to use is the 55 nanoseconds version. It's going to have a total read cycle time and write cycle time of 55 nanoseconds, which you can compare to the 150 nanoseconds of a ROM chip. So this one is going to be almost 3 times as fast. And we'll take a look at the timings in detail later in the video. So one specificity of the RAM chip that I want to point out is that the write of the data is actuated when the write enable pin goes high. So we didn't talk about the write enable pin last time for the ROM because we are not going to be using it. But the write enable works just the same as the output enable, except that the data is latched when the pin is rising. We're going to need to manipulate this pin precisely in order to know when our data is being written. And we'll talk about that later in the video as well. So let's go into KiCad and add the RAM chip to our schematic. Okay, so this is our schematic where we left off the last time. Let me update the date and the revision. This is episode 15. So let's go into the memory module and we'll add the RAM. This is the one. And we're gonna need the data bus for the outputs and the address bus for the address lines. It needs a decoupling capacitor. Then the chip select is going to be the RAM chip select. The output enable is going to be the same as the ROM because if we're in the right address, then the read works identically to the ROM. And then we need the write enable pin. And so for that, I'm going to create a new signal, which I'm going to call WR for write. And I'm actually going to rename the other one to be RD for read. And both of them are active low. Let me update this. This is RD. Then we need the correct input pins for this module. And we need to import the write pin and the RAM chip select. There we go. So this is the new memory module. Let's go level up and import the new pins. So let's go into the glue logic and update it as well. So now the question becomes, how do we generate this signal? And I'll talk about that in a minute. I just want to also update the address decoding sheet. So for now, the RAM chip select is going to be connected directly to A15. It's the inverse of the ROM. So when we are not talking to the ROM, we are talking to the RAM. And so for now, I'm ignoring the I/O range, and I'm also ignoring the bank 0 signal in the address decoding circuits that we built 2 videos ago. I will flesh the circuit out in a future video. So this is our RAM chip select. Let's import it. Let's also import those pins here. There we go. So now the only thing missing is what we're going to do with the write pin. Okay, so let's take a look at the timing of the SRAM. And I'm going to be starting with the read cycle, which is going to be pretty similar to what we saw in the last video. So if you haven't seen that one, I encourage you to check it out because this is going to be pretty much identical, and I went into a lot of detail in the previous video. For the SRAM, there are two types of read cycle. The first one is address controlled, and that means that you keep all the control lines enabled and you only change the address and you go through varying address values. And so this is not the cycle we're going to be using. We're going to be controlling the chip enable and the output enable in each clock cycle. So this is the cycle that we're going to be interested in. So let me get started on the timing diagram. Okay, so this is the basic state of the bus. I'm basing my diagram on a 4 MHz clock, which is our target. We have the clock here running for 250 nanosecond each period. The address and the read-write signal of the CPU is valid 10 to 30 nanoseconds after the falling edge of the clock. And we have computed in an early video when the CPU is reading data and when we have to present data to the buffer. And that's going to be 19 seconds before the falling edge of the clock and 9 seconds after the falling edge of the clock. So this is where the data has to be valid because it's being read by the CPU. So in a read cycle, we're going to be using the read signal, and this is going through a 74HC10 at the moment, which means it's going to be valid 10 to 54 nanoseconds after the falling edge of the clock. Then the RAM chip select is going to be the value taken from our address decoding circuits. Again, we've computed this value in a previous video. So the first value we're going to be interested in is TAA. It's the time between the address being valid and the data being valid. This in the datasheet is 55 nanoseconds. So let me add this to the diagram. So 55 nanoseconds after the address is valid. The second value is chip enable access time. And so that's going to be the delay between the chip enable being valid to the data being valid. So let's add this. And that's going to be 55 nanoseconds as well. So it's going to start after the chip select is enabled here. The next value is the output enable access time. That's going to be 30 nanoseconds. And that's going to be the time between the output enable going low and the data being valid. So let's add this to the diagram. And here we have the time T output enable. From this, we know that we're going to be taking the maximum of those timings, and that's when the data is going to be valid. So let me add the RAM data here. So as you can see, the maximum is here, and we know that over here, the data is going to start becoming valid. Now, when does it actually turn on? The datasheet says that there is a chip enable to output in low Z, which is 10 nanoseconds. And an output enable to output in low Z, which is 5 nanoseconds. Each are minimums. So let's add that. As you can see, the minimum is 5 nanoseconds after the read signal becomes valid. And so the RAM is going to be in high impedance until this point. Then we have the chip disable to output in high Z and output disable to output in high Z. Those start at 0, but can be a maximum of 20 nanoseconds. So let's add this one. So as you can see, we have 20 nanoseconds for the output to turn high Z after the first of either the chip enable or the output enable triggers. Then we know the chip is disabled. So this happens here, and it can start happening right away. So the minimum of those two is 0. And so this is why I've put 10 nanoseconds here, because this is when the read signal is going to start changing. So as you can see, we are pretty good with the timings of the buffer on both sides. And so we're good to add the RAM as is. Now let's talk about the write cycle. Okay, so I'm here in digital, and we're going to be working on the read and write pulse circuit. So the first thing I'm going to do is I'm going to add inputs and outputs. First input that we have already seen. This is the read-write signal. And in terms of outputs, we have the read pulse. And in this episode, we're going to be also working on the write pulse. And for now, what we have done is we've used a 74HC10 to invert read-write and go into read. And we don't know what we want to put here. So let me add a test case. And let's say, so we have read-write here. It can be 0 or 1. what do we want read to be and what do we want write to be. So for read, it's pretty simple. It's just the inverse. And then for write, it's identical to read-write because read-write is low when we are writing. And so that's the same for WR here. So let's do this one. So for that, we basically just have to connect it like this. Sorry, I made a mistake here. I said this is the inverse. Okay, so this is the naive version. Now, the problem is in the datasheet of the RAM. So again, there are two types of write cycles. The first one is write-enabled controlled, and the second one is chip-enabled controlled. And the only difference is the order in which chip-enable and write-enable are toggling. But what we have to notice is that in each cycle, the data is latched when chip-enable or write-enable have a rising edge. And so that's going to be the earliest of the two that are going to be triggering the latch. So one number that is really critical here is the TWR here. And that's the time between the write-enable having a rising edge, so the data being latched, and when we can change the address at the input pins. And if you look at the timings, TWR, the write recovering time is a minimum of 0 nanoseconds. And so that means that the address pins can't start changing before the write pulse is finished. So if we take a look at the timings of the CPU, we know that the address pins and the read-write pin are valid from 10 to 30 nanoseconds after the falling edge of the clock. But it doesn't really specify in which order those signals change. And it's totally possible here that the address pins would start changing before the read-write signal. And so this would be a problem with the RAM because if you don't follow this timing, this TWR here, it's possible that your write is going to be happening at the wrong address because the address is already going to start changing when the write happens. So we have to control the order of this pulse here. And the way to do that is with the clock. And so what we're going to do is we're going to say, well, we only want to be writing when the clock is high. This way we're going to have a rising pulse here when the clock is falling. And then it's going to give us 10 nanoseconds before the address starts changing. So let me add it to the diagram here. Okay, so here I've added what the write pulse could look like. So as you can see, it's kind of the inverted clock. But obviously it's only going to go low when we're writing. But the way it would work is if we can guarantee that the rising edge happens here before the 10 nanoseconds where the read-write signal starts changing, then we're good for the writes and we can write to the RAM properly. So let's go into digital and see how we could design this. We're going to need another signal, and that's going to be the clock. And if we update our test case to include the clock is going to go from 0 to 1. It's going to look like this. So when we are reading, we want read to be low and write to be 1. And when we are writing, we want read to be 1 and we want write to be 1 on the first half of the clock cycle and 0 on the second half of the clock cycle. So this is the signals that we need. And the way to do that is with an OR gate, read, write, or the clock. And so when both of these are low, this is going to be low. And actually we need the inverted clock here. So now when we are writing and the clock is high, this is when the write pulse happens. So let's add this to KiCad. So we're going to go into our glue logic and we have a few OR gates here that are remaining free. So this is what I'm going to use. And as we saw, we need the inverted clock and read writes. And this is going to give us our write pulse. There we go. So let's add this to the timing diagram properly now. There we go. So the propagation delay of the 74AHT32 is 1 to 8.5 nanoseconds. So this is well within the 10 nanoseconds that we need for this pulse to happen. So we are good on that front. Now let me finish this diagram. So this here is the write buffer. This is a value that we have computed in one of the previous videos. And it's going to be the time when this CPU is writing data to the bus and when the buffer is making it available on the data bus. And that's happening 39.5 nanoseconds after the rising edge of the clock and until 10.5 nanoseconds after the falling edge of the clock. So this is when the data is available on the data bus. This is our RAM chip select. We've computed it to be 76 nanoseconds in a previous video. And now we can take a more precise look at the timing of the RAM in a write cycle. So we're going to be in the write cycle 1 because our chip enable is happening way before the write enable. So this is what we're going to be focusing on. So our data needs to be valid in an interval that is TDW to TDH. So TDW is data to write time overlap. That's going to be a minimum of 25 nanoseconds. And TDH is the data hold from end of write time. And that's going to be a minimum of 0. So we need to present the data 25 nanoseconds before the write pulse is happening. So this is when the RAM is reading data. As you can see, it's 25 nanoseconds before the earliest where the write pulse could happen, and that's 1 nanoseconds after the falling edge of the clock. So that's 24 nanoseconds before the falling edge of the clock here. And then the whole time is 0 nanoseconds after the latest point where the write pulse could happen. So this is where we need the data to be valid. As you can see, it's valid at the right times. Okay, so let's add the remaining timings. So TWHZ and TOW we are not going to be using because these are related to what happens if you leave output enable high before or after a write, and we're not doing that. Then we have TAS, TWP, and TWR. These regulate how the write enable pulse can behave as it relates to the address bins. TAS is the address system time. That's a minimum of 0. TWP is the write pulse width. That's going to be a minimum of 45 nanoseconds. And then TWR is the recovery time. That's going to be 0 at the minimum. And so what that means is we can't trigger the write pulse before the address bin is settled. And that's what we are currently doing. Then we have a maximum of 45 nanoseconds here for the write pulse. And then we can't change the address bins before the write pulse is finished. And so let's add this to the timing diagram. Okay, so I've added here the write recovery, the address setup, and the write pulse minimum width. And as you can see, we are meeting all those requirements. Then we have TCW and TAW. TCW is chip enable to end of write, and that's the time between the chip enable going low and the write pulse finishing. That's going to be a minimum of 15 nanoseconds, and same for the address valid to end of write. The address needs to be valid at a minimum of 15 nanoseconds before the write is finished. So let's add this to the timing diagram. And I think I'm going to invert here RAM chip select with the write pulse because all the data is going to be for the write pulse. Okay, so I've added the TAW and TCW, and as you can see, we are meeting those values easily because the end of the write happens here. Okay, so I believe this is everything we need for the write cycle. So as you can see, we are meeting all the requirements at this frequency. We could go quite a bit faster before we would hit any limit, but we're now able to write to the RAM. And so let's go into the breadboard and implement this new circuit. So this is our breadboard where we left off the last time. The first thing I want to do before adding the RAM is I want to move the read signal generation from this NAND gate over here to this one over here. And then we're going to be able to use the OR gate that I have here to generate the write as well. So it makes sense to have it on this breadboard here. So let's do that now. So I'm going to remove those two control lines. Those are for ready and for bus enable. But we do have pull-up resistors here and here. So I don't think those are needed. Let me turn off the power. Okay, so we have our read signal coming over here next to the emulation LED. I'm gonna bring it back down here to the spare NAND gate that we have here. So this is going to invert it, and so that's going to be our read signal. So I'm going to use this wire here to get it to the ROM. And of course we're not using these inputs anymore, so we can tie them high. So this should still work. And it does. Perfect. Let's generate the write signal. So I'm going to use the OR gate that I have here, and we need to OR the read-write signal with the inverted clock. So this is read-write. This is the inverted clock. And this is going to be our write pulse. I'm going to put it here for now. Let's add the RAM. So this is the RAM chip I'm going to use. So it needs power and ground, and a decoupling capacitor. And then the pinouts is exactly the same as the ROM, except for the control signals. So I'm going to take the data bus over here and the address bus over here. So I have cut all the necessary cables. Let's plug them in. So the read pulse we can take across to the ROM here. And then this is the write pulse over here. And then temporarily we have connected A15 to the chip select of the RAM, which is over here. And there we go. So this is our RAM connected. Let's turn the power back on. And it looks like the ROM is still working. So now what we have to do is write a program that allows us to test the RAM. So let's do that now. Okay, so I've written a test program here that's going to be able to exercise the RAM. So let me walk you through it. So the first thing we do is, just like in the last video, I set up my output file and the format to plain. So it's just going to be plain binary. My CPU is 65816. And all the uninitialized memory, it's going to be EA, which is a NUP. Then at address 8000, which is the start of our ROM, we have the main loop. First thing we do is put the CPU in native mode. For this, we use the CLC and XC instructions, just like we saw in the previous videos. The next thing we have to do is we have to set the registers to 16 bits. By default, even in native mode, the A, X, and Y registers are still 8 bits. And you have to set bits M and X to 0 in the CPU status register in order to enable 16 bits mode. And so what the RIP instruction is going to do is going to clear the bits that are set to 1 in the immediate here. And so these are M and X. Then we have two assembler directives that are going to tell the assembler that starting now, the index registers are 16 bits and the accumulator is 16 bits as well. Then we're going to put into the X register the address for the end of the RAM space. That's going to be 7FFF. And we're going to decrement it in order to align to 16 bits. Since we're operating in 16 bits mode, the address should be an even number. Then we go into a main loop. So what we're going to do is we're going to store the X register at the address pointed by the X register. So it's going to store 16 bits of data, which is the contents of X. And it's going to store it at X and X plus 1. Because the data bus is 8 bits, we have to store it twice, the high byte and the low byte. And we're going to verify that we read the same thing by reading the data back and comparing with what's in the X register. So this is what we do here. The first thing I do is I transfer X to the accumulator. So we're able to store the value and use it in the compare. Then we're going to store that value at the address pointed by the X register, and we're going to compare it with what's in the accumulator. So this is going to do a write, and this is going to do a read. And if the values are not equal, we're going to jump to the fail label. And the fail label is just going to put the CPU in the wait state. And we should be able to notice that on the breadboard because the wait LED is going to turn on. If we have read the correct data, we want to continue the loop, but first we have to decrement the address twice in order to go to the next 16-bit aligned address that we want to write to, and then we jump back to the loop here. At the end, once we have decremented X all the way to 0, so we've written and read the entire memory, we stop the CPU. Let me assemble this. Looks like it's assembling fine, and we can program it. And let's see if it works. Okay, so let's execute our program. So I've created a listing of the program here. You can see on the left the program counter, the hexadecimal version of the instruction, and then what is it in binary. So you will be able to follow as the CPU executes code what happens. So let me put this in place of the clock here so it's on camera. All right, so at the moment the CPU is reset. So let me load the first instruction. There we go. So the first instruction is CLC, clear carry. Then we are loading XCE, and so this is going to put the CPU into native mode. You'll see that the emulation LED will turn off. There we go. Then we are going to enable 16-bit mode in the CPU. This is the RAP instruction, which we are loading here. And then we are going to load the immediate, which is here. And so this works. You can see only a valid data address has lit up here. And so this is not an opcode, so it's the immediate. Then we are going to set X with the end of RAM. So this is what we are loading. And then we are going to load 11111 and then 7F. And then we're going to the loop. So we are going to transfer X to A. Then we're going to store A at the address that is pointed by X. So we are storing at the moment 7FFF at 7FFF. So we will see a write. So we're loading an instruction. And then this is the write. So, okay, so at the moment the data is off because this is the low clock cycle, but remember the write is only active. The CPU is only writing data when the clock is high. So let me press the button here. And you'll see that the data bus lit up with the data that we want to write. That's FFF decremented one time. But you'll also see that the bank address lit up. And so that's curious. I think what's happening here is because I'm using just some random families of chip here on this breadboard, there are HC families, so they're really slow. And as we saw in the timing diagram of the CPU, the latching of the bank address is really sensitive to the speed of the chips. And so what I think is happening here is that potentially we are latching what's present on the data bus. So we'll have to fix that. But since we're ignoring the bank address in the RAM circuit, everything should still work fine. So let's do the write. I'm going to release the button now. Then we're going to load the next instruction, which is the compare, which you have here. And then 0. And then we should be reading from the address 7FFE, and we should have the same data that we just wrote, which is correct. And so because the data is the same, it's going to continue the loop. And so it's going to go into decrement. And as you can see, we have the decrement instruction. No, sorry, we are loading first the branch not equal. And it's not going to trigger, and so we're going to continue to the decrement. So this is the address of the branch. And we're now loading the decrement. We should do it twice. There you go. Then we have another branch, which this time we're going to take. And we're going to go back to the takes A. Yep, that's correct. So everything is working. The only curious thing is the bank address here getting latched. You can see it's latching what's on the data bus. And so probably this is going to be fixed by replacing those chips. Let me do that now and try it. So I have here HC11 and HC32. Let me replace those chips here. So this was an HCT version, which is quite slow for what we're trying to do. And this was an HCT11, which is also quite slow. There we go. Let's try this again now. So let me do the write. And as you can see, we are not latching the bank address anymore. So this was a correct fix. Now the glue logic here is much faster, and so we're able to latch the correct bank address, which is 0, at the right moment here. Okay, so I'm going to let the program run, and then it should stop the CPU when it's finished, and if there's an error, it should raise the wait line. So let's do that. So this is running now at the maximum of the slow speed, but it's still pretty slow, I guess, to go through 32K of RAM. So let me go into the fast clock, and it's done. And as you can see, we have reached the stop instruction here. No, not actually. Yeah, I think we have stopped the CPU, and then it's incremented the program counter, so we see the weights here on the data bus, but the CPU is stopped. And if we want to restart it, we have to reset, and then we can do that again. Okay, so it doesn't look like our program has detected a problem with the memory. Let me just make it fail just to make sure. So I'm going to take one of the data bus lines of the RAM, and I'm going to force it high. So it's always 1. Let's now run the program and see if it detects a problem, just to make sure. There we go. So it's running now. And yes, this is the wait LED, and this is ready, being pulled low. So as you can see, the CPU is now waiting, so it has detected a problem here. Awesome. Okay, so the last thing I want to do before we conclude is I'm actually going to remove those DuPont cables, because they kind of take all the space in the frame and you can't really see what's behind them. So I'm going to cut good old regular wires and wire it like this, and I'm going to do this off camera. So let's do this now. Okay. So that was a lot of wires, but I think it looks better now, and you can better see what happens on the breadboard. So it's better for the videos, I think. Okay, and our program is still working. Let's speed it up, and you can see it ends by stopping the CPU. So that still works. Okay, so in this video we've added the new RAM, and we've written a test program that circles through all the memory addresses and writes and reads back some data to check that the RAM is working. In the next video, what I want to do is I want to finish implementing the address decoding logic here. You can see it's a temporary circuit for now, but we're going to need it when we go to the extended RAM. So I'm going to finish this, and we're going to be doing some reworking in digital of this circuit and implement it on the breadboard. So I hope to see you there. I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback, and I hope to see you in the next one. Goodbye.